So this is I present to joint work with Grigory Ryabov about the DCI groups, and first I would like to start with the basic definitions. So we are talking about Cayley digraphs and Cayley graphs. So this is just a usual definition for Cayley digraph. So we have a group G and a set S, and we will construct a graph with vertex at G, and we take the directed edge from G to S times G, where S is from your set. And this way we get a regular digraph. And I also listed some basic properties of this digraph. So this is undirected if the set is closed with respect to inverses. Also, this group has a automorphism group, which consists of the right multiplications. You can check immediately that these permutations maps arcs to arcs. And the last property, which is also very easy to check and well known, that if you take an automorphism of the group, then the Cayley digraph defined by this image of S under this automorphism give you an isomorphic copy. And these two graphs we call Cayley. I will use the terminology Cayley isomorphic. Now you can automorphism, and this is an example, a small example of two Cayley digraphs over the group Z8. The valency is 3, and I draw the graph for you. These are the two digraphs. You can check easily. It's not very visible, the arrows, but these are directed graphs. And you can check easily if you switch these two, then this directed force cycle maps to this directed force cycle. Switching these 1 and 5, the directed force cycle here on the left goes to the directed force cycle to the right. And because the black edges are just from a breeze graph, it doesn't affect the black edge. This is an isomorphism. And it's also easy to check that there is no automorphism of Z8, which maps this free element, this set of free elements to these free elements. So this is an example, isomorphic Cayley digraphs, which are not Cayley isomorphic. And because of this example, we can speak about CI subsets. We can make the following definition. We call that a subset S is a CI subset if the isomorphism between the Cayley graph defined by S and some other Cayley graph defined by T implies that the set T should be the image under some automorphism of the group. Or so to speak, the isomorphism, is it true that the isomorphism always implies Cayley isomorphism? And we can speak also about the DCI group, if this is true for any subsets, and we say that the group is just a CI group, if this is true for the inverse closed subsets. So for example, in the example, this is not a DCI group. We have digraphs which are isomorphic, but not Cayley isomorphic. But if one restricts only to undirected graphs, then the isomorphism always implies Cayley isomorphism. And this question was raised first time probably in the literature by Peter Babai and Laszlo Babai and Peter Frankl. They asked which are the finite CI groups. And this turned out to be not a very easy question. And this initiated quite intensive research. And Tsai-Heng Lee much later wrote a survey paper about this activity. And in his survey paper, he also posed the same problem, but he also posed for DCI groups. So I will like to review the known results. So the story, in fact, started by the research problem of András Ádám. He asked, is it true that any finite subgroups are DCI groups? And there were examples, like Z8 is an example, but there were many other examples constructed soon after the problem was published. But remarkably, the classification of cyclic and DCI groups were obtained only 30 years later. And this was done by Misha Mozichuk. He wrote more papers, and I put the year of the last paper. And he proved that a cyclic group is a CI group if and only if the order is K or 2K, where K is a square free number, or one of these three numbers. And it's a DCI group if and only if N is a square free or 2 times square free number. So after that, I would like to present the possible candidates. So we're done with cyclic, we are interested in other groups. And for the other groups, there are some possible candidates. And first of all, for the non-abelian groups, we need a definition. For the non-abelian groups, I will denote by E of Mn, the semi-direct product of group M with group L, where M is abelian of odd order, and each of its zero subgroup is elementary abelian. L is a cyclic group whose order is very restricted, plus co-prime to the order of M. And the action of L on M is defined in the last point. So if L is generated by some element Z, then Z acts on M by inverting its elements if the cyclic group has even order. And if the order is free, then you can write the action here on the elements. And it turns out that these actually, essentially, these are the only non-abelian candidates for a group to be CI, and accumulating the work of several mathematicians, the following list was constructed or was proved by Ping-Jing Lu and Peter Palfi. So if G is a finite CI group, then it follows that G is either a direct product of three groups of pairwise co-prime order, where G1 is abelian with zero subgroup is elementary abelian or Z4. G2 is one of these non-abelian groups or the trivial group, and G3 is one of these non-abelian groups of the trivial group. So this is quaternion, this is just alternating group. And this is the first family, and the second family consists of these groups. The non-abelian group semi-direct product E of M8 plus a few finite groups, and this actually division of the family was distinguished upon the elements of order 8 or 9. So in my talk, I will focus on the abelian CI groups, and I just recall the result again for the abelian case. So for the abelian CI groups, we know that each zero subgroup is elementary abelian Z4, or we have one of these groups, CI groups. I just mentioned that all confirmed CI groups in family 8 are also DCI, and these are not DCI. So in the rest of the talk, I will focus on DCI groups. And also I introduced this notation for the class of finite abelian groups, all of whose zero subgroups are elementary abelian Z4. So the big question, which are groups here are indeed DCI? And this turns out not an easy question. So first, let's start with elementary abelian. So elementary abelian case, the cyclic group of order P was proved to be DCI by Djokovic and also Elsbach-Turner. It's actually not very difficult. And later, Chris Gottsell and Brian Aspect and Louis Novitz in a paper 1999, the confirmed CP, the group of rank 2. The group of rank 3 was proved to be DCI by Ted Dobson. In fact, Brian Aspect and Louis Novitz proved these two results in the same paper, and they simplified the previous proofs. So the goal was to write a more simple, more elementary proof. All these proofs are based on permutation group theoretical techniques. Then round 4, Mitsuko Hirasaka and Misha Mozichuk, using Schur rings, they managed to prove that elementary abelian group Cp to the 4 is DCI. And again, later, using permutation group theoretical techniques, Joy Morris found another proof and published it in 2015. And quite recently, Yang Chuan Feng and myself, we proved that the elementary abelian group of rank 5 is DCI. Unfortunately, or I don't know, the pattern doesn't continue if the rank is larger than 5. And first, Ruiz-Novitz constructed a Cayley graph over elementary abelian group C2 to the 6 and showed that this is not a CI graph or not a CI subset. And that shows that this group is not a CI group. With computer, Pablo Spiga managed to find a counterexample over the group C3 to the 8. And the best general bound now is due to Gabor-Chomley, who proved that if the rank is bounded by 2p plus 3, then the group is not a CI group. So for elementary abelian, it's quite open, the answer. If the group is not elementary abelian, we have the following results. So I denoted by omega of over G, the total number of prime divisors of G. And if we go with this, if it's 3 pi divisors, then there is one group which is non-cyclic and not elementary abelian. And for that case, with Misha Mudachuk and myself, we proved that the group is indeed a DCI group. And we can conclude that all groups with at most 3 prime divisors are DCI. With 4 prime divisors, there are 2 recent results. One of them was obtained by Misha Mudachuk and Gabor-Chomley, and they proved that that group is a DCI group. And also recently, these are both are on the archive. Grisha Ryabov proved that this group is a DCI. So here we have this is a missing group. It still has to be done. And if we go with the number of prime divisors larger or at least 5, we have a recent result with Grigory Ryabov that the elementary abelian group Cp to the 4 direct product with CQ is a DCI group. And I would like to mention that Ted Dobson derived further DCI groups, assuming certain constraints on the prime divisors, and this is his result. So if G is a possible candidate, and the order satisfies this condition, then G is a DCI group. He managed to prove that for general N with this condition. And I would like just to pose this question, or maybe a conjecture, we can also call conjecture, so far no counterexample, that is it true that G and H are abelian DCI group with co-prime order, then the direct product is DCI group. So to prove this, to answer this question in a positive, would reduce to the problem to the elementary abelian groups, which would be, I think, would be a very serious step towards the final answer. So I would like now to turn to the method. So I told you that we use, Misha Mudachuk and Mitsugo Hirasaka use Schur-rings, and this we also, in our papers, we use the Schur-ring method, and I would like just to introduce further Schur-rings. So what a Schur-ring is, take a group. Now, for a subset X, I will denote by underline X, the corresponding formal sum in the group ring. And now a Schur-ring is just a subring of the group ring. If you can find a partition S of A such that the set containing the identity element belongs to the partition, any class if for any class, its inverse is also in the partition, and the group ring element corresponding to the classes generate your ring. So in the classes, we code the basic sets of the ring, and the cardinality of the partition is just the rank of the ring. So the simple examples, the trivial example, the full group ring satisfy this condition. And if you take just two classes, sometimes this is called trivial S ring, and the rest, it's also a Schur ring. And why Schur ring is interesting? So the definition is motivated actually by a result of Schur. So let us denote by sup of GR the set of all permutation groups of G, which contains the group of right multiplications. So the set of all overgroups of GR, if you want to say, and Schur proved that for any such permutation group, if you take the orbits of the point stabilizer, the corresponding group ring element generates a subring. Clearly, this subring satisfies all the axioms which we saw in the S ring definition. So it's a partition, any X inverse, just the paired orbit, if you want to say, and also the identity element is clearly just one orbit of the point stabilizer of the identity. So this clearly is an S ring, and this S ring is also called the transitivity module over G induced by A, and I will use this notation. Well, not all S rings are transitive modules, and because of that, it makes sense to say that an S ring is Schurian if it can be obtained by Schur theorem. So there is a permutation group such that the orbits generate the basics, the orbits from the basic sets. There is some terminology and S rings. So we just say a subset is an A set if the corresponding group ring element belongs to the ring, and the same for the subgroup. A subgroup is an A subgroup if it is an A set. The subgroups, the A subgroups form a sublattice of lattice of all subgroups, and you can also introduce sections. So if you have a subgroup U containing normal subgroup L, then we say that a section is an A section if both U and L are A subgroups. And whenever we have an A section, it's possible to define an S ring on the section in such a way that we take the projections of all the basic sets contained in U under the canonical epimorphism. Okay, before I give you an example, I just want to introduce one more terminology, and this is the cycloatomic S rings. So this is the case. So when we take a transitivity module induced by a group contained in the holomorph. So now A is just a semi-direct product of the group of right multiplications with a subgroup of the automorphism group. And in that case, we also use this notation for the transitivity module. So this is a cycloatomic S ring. And if this is the example, if you take the group of elementary abelian group of rank 3, then the automorphism group of matrices, still a pizza group is given here, just this upper triangular matrices. And if you compute the orbits of this group, then you can find that it fixes exactly P elements. This gives you basic sets of size 1, and they live in an A subgroup of order P. This is U1. Then you have another subgroup, other two subgroups fixed by this of order P square, and of course the full group. And that means you have a chain of A subgroups, and it also turns out that any orbit or any basic set contained in such difference is just a coset of a subgroup of Ui minus 1. So in that case, and these are all the subgroups, all the A subgroups, so the lattice is a 3. It's a well-known fact that it turns out that for an S ring A over G, the Cayley digraphs, when X runs over the basic sets, induce the basic relations or the basic graphs of an association between point G. This is also called Cayley scheme. And we can define isomorphism between S rings as isomorphism between Cayley scheme, between association schemes. So an isomorphism from an S string A to an S string B over some other group H is just a bijective mapping from G to H, which maps any basic graphs to some basic graph of the other S string. We say that F is normalized when it maps the identity to the identity element. And I also need this notation for the set of all isomorphism A to an S string over G. So basically we are interested in S strings, isomorphism between S strings over the same group. And I sometimes use this notation for the isomorphism containing all the normalized ones. So this is again, let's go back to the previous example. So we had this Sylow-free subgroup, and we know that they generate an S string with a lattice, with A subgroups of a lattice. Now look at not the whole group, but just look at the subgroups which is of order at must be. So there is a trivial one. That means the lattice is just the lattice of all the groups. So the lattice is the lattice of all the groups. So the group of order P are just the points of a projective plane. The group of order 2 are just the lines of the projective plane, and the lattice is just the incidence. Between here, we just get to see the incidence graph, nothing more. If the group is order P, there are two options based on the Jordan normal form. The group generated by this one has this lattice, and the group generated by this one has this lattice. And here, the difference, why I call it exceptional, and this will play an important role for us later, is that here every basic set is a coset, but here it has a subgroup of order P containing all the singletons and basic set. You have an A subgroup of order P square. The basic set here are the cosets of this subgroup. And the basic set, which is not contained in this A subgroup, the remaining basic sets are all of order P, and they all generate the whole group, but they are not cosets. So this is true if P is odd, of course. So in that case, for example, if P is odd, this is true. And this, we call it exceptional. This will be important later. Okay, so these are isomorphisms, and now we can define a so-called automorphism group of the S string. So first observation that the isomorphisms are clearly not a subgroup in general, but they contain a subgroup consisting all isomorphism from A to H Cyclic graphs. So this is just the intersection of the automorphism of the Cayley graphs, and this intersection is called the automorphism group of the S string. So this definition is due to Misha Klein, and one can observe that if you take any overgroup of GR, then the automorphism group of the corresponding shooting is nothing less but the two closure of the group. So I will denote this, I will introduce this notation for the set of all overgroups which are also two closed. And we will also use the well-known fact that actually any automorphism group of any Cayley graph is a two closed, it belongs to this set. So now we can define CI strings, which will be our main tool for the CI problem. So you can observe, it follows from the definition that an automorphism composed of the ring composed with an automorphism of a group is always an isomorphism. Now we call A is a CIS string if equality holds. This definition was introduced by Mitsugo Hirasaka and Misha Modichuk. And just one can prove easily that this equality actually is equivalent with this equality. So we need to consider, it's enough to consider only normalized isomorphisms. And just a simple observation, which we also, but it's useful sometimes, that we know that isomorphisms are not groups, but if the CI string is normal, which means the group of right multiplications is normal in the full automorphism group. In that case, actually, this equality becomes just, this product just gives you the full automorphism groups. So for normal CI string, the isomorphisms are just the group automorphisms, and they behave nicely. And this is sometimes useful when you don't know that the full string is normal or not, but some quotient is normal or sub string is normal, then you can use it. And this is the rephrasing of the definition, which I call simulation property. So an string is CI if and only if for each normalized isomorphism, you can simulate by some automorphism. So there's an automorphism alpha such that the action of f, the image of phi or on x is the same as the image under alpha for any basic set. So this is just the follows from the definition. But sometimes when we use that an S-string is CI or not, sometimes for certain S-string, this is useful property. You can use this, and we will see examples later when we go on this way. So why CI S-strings are important for us? They are related to the DCI groups because of the following two results. So first of all, I call an over group is GR transjugate if it admits exactly one conjugacy class of regular subgroups isomorphic to G. And Babai proved that actually gave the following group theoretical criterion for a subset to be CI. He proved that a subset is CI if and only if its automorphism group is GR transjugate. Actually, Mitsubishi Hirosaki and Misha Mudachuk proved that if A belongs to a two clause overgroup, sorry, this should be GR, then A is GR transjugate if and only if the corresponding Schrödinger is CI. These groups are too closed, so they belong to, they covered by the theorem of Misha Mudachuk, and this gives you a corollary that if you can prove that each Schrödinger S-string over G is a CI S-string, then G is a DCI group. So sometimes the idea behind it is that sometimes to see that a Schrödinger is CI can be read out of the structure without knowing any without using full effects. What kind of structure we can be used for Schrödinger. So the first is just an observation, simple observation, that so you have to look at the transjugability property of two closed groups basically. And in connection with this, you can define the following relation. So if you take two over groups of G sub R, then you can say that one is GR complete subgroup of the other. If for any permutation, if GRF is conjugated in B, then it can be conjugated inside A using some element of B. So then this relation gives you a poset, and clearly it is clear that for the GR transjugate property, you have to look at the minimal elements of the poset. Because we are interested in two closed groups, we also sometimes look at the minimal elements on the poset on the two closed groups. And with Misha Mudachuk, we had this small lemma. So if you take a group A, which is minimal in this poset, and look at the corresponding S-string, then if it happens that the S-string has an A subgroup such that its index is a P group, then the quotient S-string should be a P S-string. So this is already a restriction on the possible structure of the S-string because you are looking at transitive modules coming from this group. The other structural property, which is useful, is a so-called star product defined by Hirosaki and Mudachuk. And it says that suppose you have two A subgroups V and W, then we say that the S ring is a star product of the restricted of the in-use S string AV with the in-use S string AW. If the intersection of the two groups is normal in W, any basic set contained in the difference W minus V is a union of some UV cosets, and any other basic set which is contained outside V union W can be written as a product of two basic sets when one is from V and from the other to W. So I will give you an example in a moment. So I just would like to introduce free mode terminology. So we say that this is not trivial, and the subgroup is non-identity and not G. And we also, if the two groups intersect trivially, then we can, this is just, we call it the tensor product, and we use this notation. And in the case when W is the whole group, we call it the Vries product and use this notation. And this is the example. So if you take this S ring as before, now we can select two A subgroups, W of order P squared and V is of order P. They intersecting trivially. And my claim is that the S ring in use on this subgroup of order P squared and the S ring in use on this V gives you the tensor product of these two S ring is exactly your ring. And for that, you have to check the axiom 3, this product axiom. And in this case, the S ring here is just the basic sets, it's just the group ring. The basic sets are just singletons. So if you multiply a basic set with any basic set in this S ring, the result, because it's singleton, it should be, it's not difficult to prove that the result should be basic sets of the whole S ring. So this third definition also satisfied. And because of that, we can say that the S ring A is a tensor product of the S ring in use on the subgroup W plus the subgroup V. Now on W, this is a group of order P squared. It has a unique A subgroup of order P. Inside here we have singletons, and outside we see cosets of this subgroup WV1. And if we go back to this definition, you can see that applying this the second axiom, we see that the V minus W1 is a union of cosets of the subgroup, which is a W1 in that case. So we see that this S string, the in-use S string, is a Vries product. And we obtained this description of our S ring. So our S ring admits this tensor product with a Vries product description. The star product is used for the CI property because of the theorem that if G is a direct product of elementary abelian groups and A is an over group, then if the corresponding S ring admits the star decomposition such that both the in-use S string AW and the in-use S string on this quotient are CI S string, then the S string is CI S string. The other product which is useful regarding the CI property of S string is the generalized Vries product. And this was defined by Sergei Yevdokimov and Ilya Ponomarenko. And first of all, we have to use this radical here for a subset. The radical is the subgroup of G satisfy this condition. So you can say that this is the largest subgroup of G such that X is a union of left and right cosets of G. And the definition is very simple. We say that an S string over G is an S-Vries product if S is a section with groups U and L, and also L is normal in G, and any basic set outside U should be a union of coset of subgroups of L. So for any basic set, the radical contains the subgroup L. Again, in this example, this S ring of order P of a group of order P square, this V's product satisfies this condition. So this is the generalization of the V's product actually, by this reason. And we say that S product is non-trivial if L is non-trivial and U is not the whole group. If S is trivial, that means U is equal to L. Then this is just the usual rest product we saw before. And we also say that an S string is decomposable if it can be expressed as a non-trivial S product and indecomposable otherwise. I have an example. So this is a very important example. I just quickly show you because I still would like to go to the end. So this is an example. Now we construct an S string over ZP to the 4 as a generalized V's product of two S strings of order P to the 3. So the one is the exceptional one, the other one is this one. And the result is this V's product of over the group CP to the 4. And actually U1 is this exceptional S string we can see here. And the quotient is this one. The quotient is here. So this is the S string here. This is the quotient. And what is important is that this S string has a subgroup of order P square, which is the basic sets are just the singletons. So this has a subgroup of order P square, the basic sets singletons, and this is the quotient, and if we lift this up, we get this group U2 here. So we have U1 is this one, and this U2 is very important because this will be very important later. And it also follows that any basic set outside U1 and U2 is just a coset of V cosets. So this is a generalized V's product. It's not an easy example, but this was very important on our proof. That's why I wanted to show you this. Now the generalized V's product and the CI property. So we don't know in general if the S V's product or generalized V's product preserve the CI property. That would be very good to know it in general. But with Grigory Ryabov, we gave a sufficient condition. And for this sufficient condition, we introduced this notation for the intersection of the automorphism group of the S ring with the automorphism group of the G. And we proved that if you have a group which is a direct product of elementary abelian groups, and A is a generalized V's product, S V's product, such that on the induced, if you consider the induced S string on U and the induced S string on G by L, then the automorphism which preserve the induced S string AS, this group can be written as a product of these two, then A is a CI S string. So that was the proof for when G is a direct product of elementary abelian groups. And this recently, Grigory generalized this theorem, also covering the class which it's allowed that the Stiller subgroup is C4. So this is the CI property. This is the important class. So now it's allowed to use it for any abelian groups with Stiller subgroup elementary abelian on C4. Okay, so actually the last ingredient maybe in the proof, which is very important, and this is a very important result proved recently by Misha Mudichuk and Gabor Somlai. So they managed to prove this very nice description of S strings over abelian groups of very special order. So the abelian group has a prime divisor Q, but Q squared doesn't divide the order of the group. And whenever you have an S string over G, you can define two subgroups, A subgroups. Q is the least A subgroup of order divisible by Q, and H is the maximal A subgroup of order corresponding to Q. So whenever you have this S rings, the following theorem is true. In this notation, A can be written as an HQ by Q with this product. Furthermore, under this condition, you can say that this S ring is a star product. And this is a very useful because in applications, these groups is just the full group and you have a description about the full S ring. So for example, this result almost immediately implies that the problem of classifying CS rings over such groups can be reduced to the decomposable S rings. Okay, in the last 10 minutes, I would like to talk about how we prove that CP to the 4 times CQ is a DCI group. So as the first step, we take a group, an overlay group, a 2 close overlay group, minimizing with this GR subgroup relation, and you take the corresponding A subgroup. And our goal is to show that A is a CIS rings, and this is done in 2 steps. The first step is the reduction of the problem to very special S rings for possible candidate to be non-CI. We reduce to the problem to generalize these products when, first of all, P should be odd. The subgroup U has index P, L is of order Q, and on the induced S ring of order P to the 3 is this risk product. And the induced S ring over GL of order P4 is the special example. So whenever we have the special S ring, we have to check that it's a CI or not. And we did it with we just verified the simulation property for A, for this S ring. So that was very technical and computational. So I will talk about step 1 first. So as I told you, with the result of Misha-Modichuk and Gábor-Somlai, we can assume that the group is a generalized risk product. Now you have L contains the order of L is divisible by Q, and U is proper, so you have this possibility for the order of the sections. And then we would like to exclude the case that 1 P and P squared happens. One is the risk product, which we know it's CI, and for P and P squared, we use the small lemma. So we say that if you have a generalized risk product such that one of the S rings A sub U and A sub J is cycloatomic, plus also AS is Cayley minimal, then A is a CIS ring. And Cayley minimal means a cycloatomic ring is Cayley minimal is actually the orbits cannot be obtained with some smaller groups inside K. So Cayley minimality means that if I go back to this property, I have just no room for not to be satisfied this condition. And so that's using this, we immediately can exclude, if P square, we can prove that these assumptions hold. So we can assume that actually U by L should be P3. So U should be P from Q, L should be Q, and also Cayley minimality implies that the induced S ring should be this product. Then we have to prove that this S ring is decomposable, and for decomposability, we prove this lemma. For this, to have this decomposability, we prove a lemma. So you have a Schurian S ring over an abelian group. LB is an A subgroup of G, and you define this group. So that means you have, this is the kernel. So L is an A subgroup. That means the full automorphism group acts on the cosets of L. So the cosets of L form a system, form a block system for this group, and you get the action on this block system. So this is the group which fixes each coset. It's a normal subgroup, and you multiply it with just a group of right multiplications. And if you manage to prove that both these S strings and these are a CI S string plus this S string is too minimal, then A is a CI S strings. And too minimality means that so this is a Shurian S string, so it's induced by some group. And if you can manage to prove that this is the unique S string, there is no smaller group which induce the same S string, then we say that too minimal. And we use the lemma which Yang-Chan Feng and myself proved later, that every indecomposable S string over ZP to the 4 is too minimal. So here is an S string over ZP to the 4. So if that would be indecomposable, that would be too minimal. That condition would satisfy, this condition would be satisfied. And we just check that these are also true, so we can assume that GL is decomposable. And we finished the step 1. We know that we have a generalized this product, and we have an S string. The quotient is a decomposable S string, and we just proved this lemma for decomposable S strings over group CP to the 4. Suppose that you have an A subgroup on which the induced S string is a Bliss product, and A has a basic set outside U with trivial radical. Then this condition holds, and this is enough for the CI according to other condition, unless you have this description of this S string. You have an A subgroup U1 and U2 of G of order P to the 3, such that on this one you have the S string which is exceptional, and U2 you will see this S string. And the step 2 is the simulation property. And now, when I will not want to talk about the details much because it's really technical, but just give you the idea how we do it. So we have to simulate. We take a normalized isomorphism, and we have to find a group automorphism for which any basic set is mapped to F. The image under any basic set under F is the same as under alpha. And what we do is we just fix generators, we suitably fix generators of R group G, and assuming that F fixes the generators, we prove that it simulates the whole group. So for example, this is the example, if F is a normalized isomorphism, and assuming that AU is also normal, and this isomorphism fixes HA, one can prove, and we show that in that case F should be an automorphism of A. And here in this case you have to use a lot of things, like if AU is normal and fixes this, then should be identity and many techniques. It's really technical, computational. And this is my last slide basically, and I just would like to thank you for the attention.
Okay, thank you very much, István, for your nice talk. Are there any questions to the speaker? Okay, I just have some maybe stupid question. Well, you said that it is unknown in general case. Is it true that S3's product preserves the CI property?
Yes.
Well, but what is your feeling? What do you think?
I think it does.
Oh, really?
Yeah.
So this means that you have some, well, some ideas why it is true.
I tried to prove it. It's, well, yes, I tried. It's not easy, but I think this is really worth to do it, because what can happen that somebody finds some new non-CIS strings, and that would be very useful to maybe to exclude the list, or somebody can get a proof, and then that would be even, it would be I think it would be a large step towards the full classification. For example, if I go back to Gabor and Misha's result, if I just recall it, if that would be true, then you would immediately get that any group which is a direct product of a group of order P with some abelian DCI group of co-prime order would be DCI. So that would be imply this, if this would be true. But I think it is true, but I have no idea how to check it, basically.
I see. So, but does this mean that it is something like a step to have classification?
Yes, that would be very interesting.
Yeah.
To yes, that would be a one step, but it's maybe first of all, it's who knows it's true, and the second, it's not easy. But that would be a yes. That definitely, I think it would be interesting to try this, to prove this.
Okay, thank you. Are there any other questions? Well, then let us thank István again for such an interesting talk, obtaining a lot of information, as old one as a new one with new results. Thank you very much.